Okay, let's start going. I'm going to talk a little bit about light-absorbing aerosols deposited on snow and ice. And here you see a nice example from the mountains in southwestern Colorado, so San Juan Mountains, where they get frequently an impact of desert dust from the Utah desert. And what you see on the snow is this reddish grayish material. And the light absorbing part in this case is largely hematite, a red substance which makes the rock in Utah so beautiful and red. But before I get going, let me back up a little bit. Both Dr. Sambarava and I are from the Desert Research Institute, which is a part of the Nevada system of higher education, the university system here. And we have two primary locations up in Reno, here the top image, and in Las Vegas, which is about a 7-hour drive to the south of us and quite a bit hotter. We are here more next to the mountains. And within the Desert Research Institute, we have 3 divisions: atmospheric sciences, where Vera and I are located, earth and ecosystem sciences, and hydrological sciences. Now, within the atmospheric sciences, we have a optics lab. We use a lot to look at optical properties of aerosols, do a lot of instrument development, and are mostly funded by federal entities like NASA, DoD, National Science Foundation, but also by states and other programs. And now let's jump into aerosols and surfaces. So what is albedo? It comes from the Latin. What's the Spanish word for albedo, Francisco?
Yeah, correct. No problem.
Same word? So in English, we call it whiteness. It's a fraction of the incident optical power that is scattered or reflected by an object or a surface. So that means if nothing is reflected, the object appears black to us. And if everything is reflected, the object seems white to us, like snow white. And in between, we have a gray object. So now what is emissivity? Every object which is not at 0 degree Kelvin radiates black body radiation. And emissivity tells you what fraction of an ideal black body it would radiate. So if a black body radiates 1 watt and your object radiates half a watt, then it has an emissivity of 0.5. And remember, the incoming solar radiation peaks at about 1/2 micrometer wavelengths, and the thermal infrared at 300 Kelvin peaks about at 10 micrometers. As you can see here on the bottom, you see the black body spectrum of the sun, and then the black body spectrum of the Earth, because the Earth is much colder. Now, what is the energy balance of the Earth? Well, the energy coming in is just the cross-section times the solar irradiance, and the cross-section of the Earth is like any sphere, roughly pi r square. And the outgoing heat, there's a whole surface area, 4 pi r square radiates, no matter if it's a day, the sunlit, or the nighttime hemisphere of the Earth. Now, if I look at the global energy flux a little bit more in detail, we have about 340 watts per square meter incoming solar radiation on average, averaged over day and night, summer and winter, on the whole Earth. And of that, about 160 watt makes it to the atmosphere, to the, Earth's surface. And on average, only 23 watts are reflected by the surface. So the surface of the Earth, and that's dominated by the oceans, is relatively dark, with an albedo of 0.15. And snow, of course, has a much larger albedo of 0.8 or something. So it's a really abnormality in the Earth. And one of the funny things is also that the surface albedo of the northern hemisphere is within measurement accuracy the same as of the southern hemisphere, although the southern hemisphere has a much larger fraction of ocean. So now, what's the temperature of the Earth? Well, if you just take an energy balance, the incoming solar radiation equals the outgoing infrared radiation, then the incoming solar radiation is just pi r square, the cross-sectional area of the Earth, times 1 minus albedo. Remember, if the albedo would be 1, everything would be reflected, times the solar constant. And the outgoing radiation is a little bit more complicated. It's determined by the Stefan Boltzmann law. It's 4 pi r squared, the total surface area of the Earth, times the emissivity and times sigma as a Stefan Boltzmann constant. And then it goes with the temperature to the fourth power. Very nice to remember. So if we set the incoming energy equals the outgoing energy, we can calculate the temperature, and magically we get something very close to the Earth's average temperature, in this case 289 Kelvin, out of there. So climate change is very simple. Only two things, the emissivity and the albedo, drives the temperature of the Earth. So why do climate modelers get paid the big bucks? Why do they prosper so much? And the reason is climate feedbacks. It's not that easy. Both the emissivity and the albedo of the Earth change with the Earth's temperature. And the simplest example is here actually case one. Water occurs in three phases: solid, liquid, and gas. And so if we heat the Earth, there will be, for example, less snow. And the albedo changes as a function of temperature. So we can't just go from simple Stefan Boltzmann. And so the snow albedo effect is very real. If we get a few degrees of increased temperature, we will have far less, especially seasonal snow. The Earth will get darker and heat further. So the actual climate sensitivity is about a factor of 3 larger than the simple Stefan Boltzmann law, which doesn't take feedbacks into account, would predict. So snow is really a critical component of the Earth's climate system. So why do we care about albedo? So the current planetary albedo is 0.29. So that means that 71% of the light is reflected, of the energy coming in. If we change the albedo only by 0.01, that's the same, it's a change in the global energy balance of more than 3 watts per square meter, and a similar in impact to doubling the atmospheric CO2 concentration. So we always hear about greenhouse gases in the public media, but we rarely ever hear about albedo, and that's where the snow really comes in. So the Earth's mean temperature is driven by its mean albedo and its emissivity, and clouds are very important for both of them too. Now here are the first measurements of the Earth's albedo by Vern Suomi, who was a professor at the University of Wisconsin, and put experiments on the first satellites starting in 1959 with Explorer 4. And his PhD student who did his PhD on this was Tom Vonderhaar, later professor at Colorado State University. And I got to meet Tom and work with him. And so here you see as a function of the latitude, plotted the solar radiation coming in, and you see a lot of solar radiation here at low latitudes, fairly little at high latitudes, just a geometric thing. And then we see the infrared radiation coming out. So you see a energy surplus in the low latitudes and an energy deficit in the high latitudes. Of course, you can't have it. And you see the planetary albedo, that the high latitudes are much whiter, reflect much more light because they have more snow and ice. And so you can't have a deficit or a surplus forever. You get to balance that. So This energy imbalance is the ultimate driving force for all large-scale atmospheric and oceanic circulations, which move energy from the low latitudes into the high latitudes. In the northern hemisphere, the typical example is a Gulf Stream. So southern Great Britain is on the same latitude as Canada, and no, it's not snowy, there are palm trees growing there. Now, how do we determine the Earth albedo? Is number one, bean counting. You can do measurements of surface albedo, cloud covers, aerosol, and everything. And the better way is really satellite measurements. And if you look at the history of Earth albedo, 1912, people thought the Earth albedo from bean counting was about 0.89. And then in 1928, there was a first satellite measurement, which got it right on 0.29, the value which is currently accepted, 0.3 or 0.29. And what satellite do you think people used in 1928? Was it an early German effort or a top secret Russian effort or something else? No, we had only one satellite in 1928, and that was the moon. And this French astronomer Danjon figured out that the ratio between the bright side of the moon and the dark side, as seen from the Earth, was determined by the amount of light reflected by the Earth, because the dark side is not directly illuminated by the sun, but exclusively by the Earth. So out of the ratio, you can calculate the Earth albedo. And people have picked that up in the last decade again, and there are a few observatories looking at that and looking at the trend in Earth albedo. So here is a sketch of this. The incoming solar radiation illuminates the Earth. The reflected radiation, also known as Earthshine, as opposed to moonshine, illuminates the dark side of the moon. Now, if you look at different aerosols, and here are two examples, the Saharan dust outbreak and biomass burning aerosol from Southern California, we see that the aerosol here, the dust, looks pretty much the same color and darkness as a land surface, but it's quite a bit whiter or lighter than the underlying ocean. So it would cause cooling here, but if it gets over clouds, which are very white, it will cause warming. And similar with the biomass burning smoke. Now let's think about what happens if this aerosol gets on snow. Well, snow is super white, and either of them absorbs some light, so they will cause heating on the snow and lower the albedo. So aerosol albedo is generally defined, we call it single scattering albedo, as a ratio of the scattering coefficient to the extinction coefficient, and the extinction coefficient is a sum of scattering and absorption. And again, albedo goes between 0, totally black, and 1, totally white. And so aerosols contribute to heating if they're darker than the scene, or in our case, the snow below, and cooling if they're whiter. So the other thing, I thought I'd thrown that out. Let's just let this go here. Now, what determines the aerosol albedo? And the first thing we think about is the material of the aerosol particles. And all the optical properties are defined by something we'll call a complex refractive index. The real part plus the imaginary part. And if you look at the wave equation here, it's an exponential. And this is just purely oscillatory. But if we add an imaginary part, this kappa up here, then we get an imaginary time an imaginary, and this means a decaying exponent. So the energy of the wave will decay and light will get absorbed. But it's not that easy. Below here on this graph, I plot the single scattering albedo for a black carbon particle of a certain size, in this case diameter half a micrometer. And what we see, yes, if the imaginary part goes very small, the single scattering albedo goes up to 1, and then it goes down. And for black carbon, we actually can go down to 0.1, 0.15. But if we further increase the imaginary part, the particle actually becomes reflectant. It becomes shiny like a metal, and the single scattering albedo goes back up to 1. Pretty funny. Then it also depends on the size of the particles. So, small particles, here plotted on the right, are generally very absorbing. The single scattering albedo goes to 0, then it increases and it peaks, and then it gets to the macroscopic realm of our everyday experience, where the albedo is not depending on size. If you take, let's say, an apple and cut it into half, even if the particle is smaller, it still has the same brightness. Well, an apple is a bad example because it's not homogeneous. Let's say a potato dumpling. So this is our everyday experience, and in the microscopic range, something completely different happens. And then there's particle morphology, and just as an example of the macroscopic range, we have razor blades, a shiny metal, very reflecting, very high albedo. But in an optics lab, often we clamp 20 of them together, and we get an excellent beam stop, which is very black. And why is that? The light penetrates between the blades and gets reflected multiple times back and forth before it emerges, and every reflection it loses power. So the morphology plays an important role both in the macroscopic and the microscopic role. Here we got this here again. And if you plot the whole thing on a log-log scale, you see nice power laws for single scattering albedo with a size to the third power. Then you get oscillations, and here we go into the geometric regime where the albedo doesn't change with size. So here we go. I'm going to skip this here. And here now we're getting on snow. Snow is snow white. But if you look at this here, this was a nice ski trip to the summit of Mount Shasta and then skiing about 2,500 meters down where we're standing now. And you see two things here, the snow nearby. It's partially grayish, and this is likely very short-range transport of mineral dust entrained here from the moraine. And then you see a reddish color here. And these are snow algae, a form of life growing on the snow in spring once the liquid water is available and the snow becomes isothermal. Now, if we look at snow reflectance on the left side for pure snow as a function of size. And with size, I mean here grain size. You see that you get this highest albedo for small particles, here with a radius of 50 nanometers, and get the lowest albedo for large particles. In this case, the largest is a radius of 1 micrometers. And the differences are not very large in the visible here on the left side of the graph, but very large in the infrared. And why is that? In the infrared, water starts absorbing spectral energy on a molecular basis, and in the visible, hardly at all. So if there's no absorption, the grain size doesn't matter or doesn't matter much. But if there is absorption, for example, with water, then in the larger particles, the light between scattering events travels for a longer distance in the medium and gets absorbed. So if we, for example, add absorption due to impurities in the visible, we get big differences as a function of grain size too. Sometimes people forget about that. On the right side, we have different spectra for pure snow, which is very white in the visible. Here, actually, this is somehow cut off. Then black carbon, which has a fairly uniformly lower albedo in the visible. Mineral dust, it really depends on the composition of mineral dust. This would be a typical iron oxide absorption in the blue and green, for example, hematite or goethite. And then here's an example of a biological system, snow algae. They're red, they look red to us, so they reflect fairly well in the red, 0.7 micrometers, 0.6, but reflect quite a bit less in the blue and green. So to summarize, increasing grain size reduces albedo, especially in the infrared with a strong water absorption, and impurities, natural or anthropogenic, reduce reflectance mainly in the visible because the reflectance is already relatively low in the infrared. And this is the end of this slideshow, and I'm going to go to the second part now, if I can find it. Part 2 here. And I guess I need to set up the, okay. Okay, can you see that now?
Yes.
Okay, wonderful. So the second part, I've done some snow work in beautiful Portillo, where you guys are now, together with Professors La Puerta and Ceraceda. And my only regrets about that was that I didn't get to go skiing. And then we've also done snow work more recently, last year in Antarctica. So last year in Antarctica, I had the pleasure to go, last year I had the pleasure to go both to the Finnish Arctic and work with my Finnish friends on what they call the soot and snow experiment. And that was end of March, beginning April 2023. And then I had the absolute pleasure to go with Dr. Ceraceda down to Union Glacier, the Chilean summer camp there in December. So lots of fun, and as Francisco knows all about the Antarctic, I'll show a few pictures about the Arctic here. And the Finnish folks have done now for quite a few years soot and snow experiments. And initially they started with what we laughingly called the salt and pepper shaker approach. They would collect black carbon aerosols from chimneys and then try to disperse it on the snow. The only problem with that is that these are very large particles. Normally smoke particles are submicron, and these were much, much larger particles. So this year we designed jointly an experiment where we deposited fresh smoke and some dust on the snow, and they're very interested in looking at snow melt too. So here's an example. We got some kids' swimming pools here and inverted them, and we set them on the snow and we pumped smoke into there. This is, for example, from the burning of beechwood. And when we lift this up, you see the snow darkened radically here. And here you get an overview of our bigger 3 to 4 meter diameter sites. And then we monitor the snow albedo, the broadband snow albedo, the pyranometer here, looking at the updwelling, the radiation reflected by the snow. And in the background, we have an additional pyranometer, which looks at the downdwelling radiation. And of course, we have one which looks at snow where we didn't deposit anything. The location here, most of the Finnish folks live in southern Finland at the coast of the Baltic here on the graph on the left. And we flew up to the capital of Lapland, the northernmost province of Finland, Rovaniemi, which is just on the polar circle here, and then drove a couple of hours to this beautiful town, Sodankala. Sounds very nice, but it means village of war. And the Finnish Meteorological Institute has had a big station there for more than 100 years. So I've known these Finnish folks since Aki Virkala participated in the Reno aerosol optics study more than 20 years ago. And he has done these soot and snow experiments on a fairly large scale, while I've worked with my former student Nick Barris on a small scale, 0.5 meter diameter deposition, where we could carry all the experiment into the backcountry in the mountains near Reno. And then in 22, Aki got in touch with me and he wanted to combine the strengths and hopefully not the weaknesses of our both of our approaches. And Jonas Svensson, who works with Aki, spent a lot of time in Reno and worked with me on instrument development too. So, and then on March, April 2023, I was in Finland and we did the actual experiment. So we developed, or are still developing, 3 instruments: apparatus for dry deposition of aerosols and snow. That has been very successful, and we've published several papers on that with Nick Barris doing his PhD on it. Then we're working on a penetrating snow optics probe where we can measure the solar flux as a function of depth in the snow. And then we're working on a snow albedometer with artificial illumination, and that's still very much a work in progress. So here's the deposition. We have 2 chambers here, and they're really galvanized steel trash cans inverted. And in one, we can burn biomass. Typically, we'll do, for example, peat for smoldering combustion and get brown carbon aerosol. And then we have a pump here, either a small electric battery-powered pump or a bicycle pump. And we move the air into a deposition chamber with a diameter of 50 centimeter, again, think an inverted trash can, standing on the snow. Alternatively, if we want to do mineral dust aerosols, we put mineral dust sieved to about 20, 30 micrometers just in a flask and give it a brief blast of pressure with a bicycle pump and push it into the deposition chamber here. And Nick has published a nice paper on the apparatus, and then we also published a nice paper on deposition of brown carbon. Here's what it looks like in the snow. Here, the big trash can is a deposition chamber. Then here we have the biomass burning chamber where we generate the smoke. And we have a longer copper coil to cool it off so we don't heat the snow. And here's the actual burning pot, which is insulated to simulate semi-infinite fire without lateral heat fluxes. Here's now the penetrating snow optics probe. It's essentially just a cylinder, very similar to an avalanche probe pole, but we have an optical fiber in there. And the entrance aperture of the fiber is here in the tip of the probe with a sapphire window above it. And then we connect the fiber to a spectrometer. So with this, we can also measure the down-dwelling solar radiation. If we point it upwards, we can measure the surface snow albedo if we point it towards the snow. And then we can get the snowpack extinction versus depth. Right now, the main problem is we need to develop a mechanical gizmo to hold it steady in the snow, especially if it doesn't penetrate very far. And our spectrometer is not sensitive enough to go deep enough. Then the integrating snow albedometer aims to measure spectral snow albedo with artificial illumination, because in general you want to go up there, you need a flat surface, which is not always available in the mountains. You need an open area, you can't do it in the forest, and you need clear sky and the sun relatively high in the sky to do good measurements. So all these problems you could get rid of if you can use artificial illuminations. And we're using an integrating sphere approach, and together with a cylinder which penetrates in the snow and is internally reflecting, mainly painted white, so none of the light escapes to the side. With the sun, it's not a problem because you illuminate all the snow, but here we'll illuminate only a small part, and some of the light which penetrates in the snow will go to the side. This integrating sphere you could also use to profile the snow albedo on a snow pit wall, and I'm sure you guys are gonna dig some snow pits. And so if you have a darker layer, you will suddenly, at that height, have a lower snow albedo. Now, in how much time do we still have, Francisco?
Yeah, yeah.
How
No
much time
problem.
do we still have? 10 minutes? Or?
Yeah, okay. The next is better.
No, I'll just go fast here. So the Soot on Snow campaign in Finland, they want to quantify the effects of different impurities on the spectral reflectance, albedo, and transmittance through the snow, quantification of water-soluble and methanol-soluble organic carbon and non-soluble black carbon, fractions of wood smoke, peat burning smoke, and diesel smoke, size distribution and fractal structure of soot particles, and effect of impurities on snow physical properties, and what happens to all these things during snow melt in spring. Now, what did we deposit? Diesel smoke, we had a diesel generator there. Peat burning smoke, we burned peat in a small oven, same with wood. And we had soil dust samples, volcanic nature from Iceland. What did we measure? Spectral albedo reflectance, transmittance spectra, did electron microscopy of soot particles, especially interested in structural changes of soot, things getting more compact as they get in touch with snow. And we're also investigating how you get the soot out of the snow into the microscope, and we're exploring both freeze drying and melting and drying, snow physical properties, and OC composition. And these measurements were started after deposition and continued till the snow was melted. Here is a motley gang, including our fearless leader, Aki Vökala here, a few students, Pavla from Iceland, Jonas, who is Swedish, and it was very cold there, colder actually than I was in Antarctica. Every morning we had minus 35 degrees and the diesel engines wouldn't start. Here is a setup. We have either a diesel generator or wood stove, then we feed it dilution air, and then comes a very important part. We have a longer tube buried in the snow to cool the exhaust so we don't melt the snow. And then we blow it in one of these big inverted kids swimming pool, call it the soot dust chamber on snow. And then we can sample the air out of there, and we have a small trailer with a condensation particle counter with an absorption instrument and different filter samplers here. And the same for with just the source change, the stove for peat and wood. Here's an overview of our deposition spot. We did these large spots you saw earlier, where each spot has a pyranometer, and then we did smaller smaller spots here where we just did temporary measurements, and then we did some really small spots with the instrument we had developed in Reno. Here's the small spots, different dusts, Arizona test dust, hematite, and then a variety of Icelandic volcanic dusts. Here's what it looks like. Here's a stove where we burn wood or peat. Then we dilute the exhaust. We have the pipe buried in snow to cool the exhaust so we don't heat and melt the snow. And then we feed it into the nice swimming pool, which was just lowered down by a crane. And here you see a little trailer. That's where all the atmospheric aerosol instrumentation is in. Here you see the swimming pool lowered from this crane onto the snow. And here Dylan is doing some samples and some measurements. And here you see the diesel generator used as a source of absorbing aerosols. Here's a trailer with a condensation particle counter, and the PSAP, which is a filter-based light absorption measurement, and Aki is sitting there. Here's the densest deposition we did birch. When we lift it up, you see all the smoke there, and you see how black the snow really got. In the background, you see more of the pyranometers. Again, the trailer, and Aki was very clever with the stove. While we were generating combustion aerosol, he also produced tea or coffee and grilled a few sausages, which was very popular. And here you see an overview of the corridors here, the pyranometers on the south, and you see again this very dark deposition of beech wood smoke. Here you see a few dust depositions which didn't work out well. We didn't get it very uniform. And here you see a good view of this really dark one. This was a dark birch wood smoke deposition. So let's look at that into more detail. And this was the most surprising thing they ever seen. So we deposited it, and initially the snow looked kind of like this here, very uniform with tiny particles, submicrometers on that. But after a few hours later, there had been some melt freeze going in, and we saw these large structures, centimeter size, and they were very fragile. But so, as much as we can figure out, we're still doing some microscopy and chemical analysis on this. Snow had partially melted, and the soot, the submicron soot or aerosols, had organized in water filaments, which then dried out, producing these centimeter large structures. And that was a total surprise to all of us, and we still don't fully understand it. And then a lot of snow samples were melted and filtered. Here you see brown carbon from smoldering combustion. You see black carbon from diesel soot. We analyzed the snow by melting it, and we had a spectrometer and a liquid waveguide. So the melt water went into this liquid waveguide, which was then connected to a light source and the spectrometer, and we could measure a long absorption path through the melt water. And here are some examples of melted snow samples from different heights in the snow. Here's the wavelength spectrum, and you see things like brown carbon, which absorbs very strongly at the short wavelengths, and other things is that water soluble, and then we also, what wasn't water soluble remained on the filter. And here's some more spectra, the height in the snow layer. So the top is the surface where we got the most effect. And here's first filtered meltwater from spot 8, smoldering peat smoke. We get very strong absorption in the UV, near visible here. And the smoke didn't penetrate very far into the snow initially. And then when we filter it, the non-soluble aerosols end up on the filter. And this here is the absorption spectrum of the dry filter then, where you see it's more black carbon, so the absorption extends further into the visible. And then we did the same thing after the spot age and see some differences as, for example, here in a methanol solution, some of the aerosols penetrated further into the snow during the melt freeze cycle. We also looked at particle morphology, and for diesel particles, we get larger particles have agglomerated when we sample them from the snow as opposed to the fresh diesel exhaust. And while we don't see such distinct difference for birch soot particles, which are more organic carbon than the diesel smoke. Now, here's the most important slide and the favorite slide of my Finnish friends. It's fun in Finland. While we were in Sodankala, we had a beautiful display of the Northern Lights one night, and you see a couple of pictures of this. It was one of the most spectacular things I've ever done, ever seen. During the 2-week campaign, we took one day off and went to the Palas National Park, about a 2-hour drive further north, and snowshoed to the Global Atmospheric Watch Station you see here on the right bottom, and the whole station is just filled with atmospheric monitoring instruments, aerosols, gases, more than I've ever seen in one location. Here we are snowshoeing up with Pavla, who's from Czech Republic but works in Iceland, and Uti, who's from FMI, and here's Jonas in the yellow shirt. And Jonas had also fun generating a snow angel. Afterwards, the experiment, Aki took me Helsinki, and we went swimming in one of the local lakes. And they keep a small spot of the lake as open water. Aki has installed a bubbler there, so the bubbles keep the water from freezing, and you can go swimming any time of the year, of course, after going to the sauna. So with this, let me end. Maybe have some discussion, and we can turn things over to Vera, which will tell us more about the chemistry of combustion aerosols. Thank you.
Thank you very much, Hans, for your overview about the aerosols impact of snow and this beautiful experiment that you make in Finland. This is a very beautiful show that we can make with the experiment in this hot spot, no, with different this swim pool. This is spectacular, no.
And this was, of course, partially motivated by the work we did in Portillo quite a few years ago, depositing diesel soot from a vehicle onto snow.
Yes, it's another scale. It's another scale.
Yes.
Yes.
And some improvements, like in Portillo, I learned that the exhaust is still warm and will melt the snow and change the grain size and the structure of the snow. And so that's one reason why we really made a big effort in Finland to cool the exhaust and prevent this from happening.
Yes. ¿Una pregunta?
I have, sí, yo tengo preguntas. I don't know if you listen to me or something.
You can listen to us.
Yes, I can hear you. Yes.
Yeah. I have 2 questions, and the first one is when you finish the experiment, what happened with the part of snow that were filled with diesel? I mean, that kept there, or you?
So the part of snow that was filled with.
What part of snow?
What part of snow? A part of snow filled with. I didn't quite hear you.
Diesel.
Diesel.
Yeah.
Yeah.
Well, one of the questions we're investigating there is as you asked, what happens with the aerosols? Initially, they get deposited at or near the surface of the snow. Then a week or 2 after we did the deposition, the snow became isothermal and meltwater went out of the snow. And so the water-soluble components get immediately washed out of the snow, which what people call an ionic pulse. Within a day or 2 after the snow becomes isothermal, the liquid water washes out everything water-soluble, and we saw that there. And then the black carbon, it is thought, and not fully explored, largely accumulates on the surface and makes the surface darker. So it doesn't get washed out. While it's very small, it's not water soluble. And right now we're planning an experiment for next spring here in the Sierra Nevada mountains of the US at Mammoth Mountain, where the US Army has a snow energy balance site. And there we have lysimeters, pans under the snow, which collect the meltwater. And so we want to chemically analyze the meltwater for black carbon and soluble things. And what we expect is that the soluble particles will come out within a day or two after the snow becomes isothermal, and the black carbon will probably come out at the very end of the snow melt. But that's something we haven't really seen yet, and I don't think anybody has really looked at it, what happens to the black carbon, but we've seen evidence that it collects on the snow surface, and that would be the same for other non-soluble things, like a lot of mineral, not water-soluble things, like a lot of the mineral dust. And in our finish experiments with the snow samples at different depths, we distinguish between the water-soluble parts in the analysis, the not water-soluble and the methanol-soluble, and the insoluble, like black carbon, which is insoluble in all organic and inorganic solvents. Does that answer your question, or start to?
Yeah. Thank you so much. And I think that the experiment is really great. So congratulations.
Thank you.
¿Otra pregunta? Yes.
I'd like to ask you, can you hear me well?
Carla, come here.
Yeah, I can hear you.
I wanted to ask you about the red algae covering the snow.
Yes.
Just I wanted to ask about the scales. If we talk about, does it have a huge impact on the snow, the algae in comparison to the carbon? In terms of scales worldwide, rather not such an important reduction of the snow production.
Well, it's very interesting. I mean, just anecdotally, when I go backcountry skiing in spring, in the areas which have snow very long, meaning in the US, let's say in April or May, you really get to see snow algae. And in some areas, they really dominate, and we don't have any good understanding in what areas. The interesting thing is that snow algae are there on all 7 continents of the US, including Africa, and they're very similar. Now, the going theory is that snow algae just spend their summer vacation on the ground, and then the snow accumulates. Once the snow becomes isothermal and there's liquid water, they swim to the snow surface and bloom and reproduce. And I do not believe that. We've taken here in winter depth profiles and analyzed them for snow algae and other microorganisms. And during winter, we saw them at all heights. So my thought is they really travel on mineral dust particles, also travel between continents. So we find snow algae wherever there's snow, and they're sitting there in the snow. And once they get liquid water, then they start blooming at the surface. And is that important? What we really need is an airborne survey of snow spectra, which can be used to identify snow algae and see where they really live on a large scale, instead of just going skiing and saying, oh, there's some snow algae. And the other thing is, I always thought of snow algae as this watermelon colored orange pink, but there are also green snow algae, we had one of the world experts in snow algae visit for a few days in Reno, and we went with him a couple of days in the mountains, and he showed me a lot of things I'd never realized or seen. So there in the US, we have now the Airborne Snow Observatory, which mostly maps snow content with a LiDAR in drainage basins. But it also has an imaging spectrometer, and that would be ideal to map out on a weekly basis where you see snow algae and answer your question, at least in a regional content. But globally, I have no idea, to be honest. But the other interesting thing about the snow algae, they're probably one of the ecosystems on the Earth which is most closely coupled to the atmosphere. So if you have atmospheric pollution and have deposition of nutrients like nitrogen and phosphor compounds, I expect the snow algae to be much more fertilized and more active. But again, this is just a thought or a theory, and there's no experimental evidence for that that I know of. So lots of work to be done.
Okay, thank you.
Okay, Hans, thank you very much for your answer and for your time and for your effort for preparation this beautiful presentation that can go overview about your work and your experiment in snow and mountains for this winter school.
Okay, very good. And now let's, Vera has probably much more interesting chemistry stuff.